string to integer, atoi, looks simple, until whitespace, signs, leading zeros, junk characters, and overflow crash your solution. This Pattern Mastery 100 Classic shows up constantly because it tests careful parsing and boundary control. Today we'll turn chaos into clarity with basic and ship an interview-proof implementation that clamps to 32-bit signed range. Breakdown. Given a string s, convert it to a 32-bit signed integer with these rules. Ignore leading spaces. Read optional plus or. Read consecutive digits. Stop at first non-digit. If no digits are read, return 0. Assess. We'll do a single left-to-right pass with index i. Track sign, plus or minus 1, and res, the number. For overflow safety, before adding a new digit d, check whether res greater than int_max//10 or res equals int_max//10 and d greater than 7, because int_max is 2,147,483,647. This runs in ON time and O1 space. Structure. Skip spaces. Read sign if +/. While next char is digit, convert to d, pre-check overflow, update res equals res 10 plus d. Return sign res, already clamped. Let's try to implement it using solution 1. We start by defining a class called solution. This is where we'll place our custom implementation of Java's atoi conversion, turning a string into an integer step by step. This defines our method myAtoi, which takes a string and returns its integer form, handling whitespace, signs, and overflow just like the classic C-style atoi function. Here we remove all leading spaces from the input string. This ensures we ignore any whitespace at the beginning, just like how reading a number on paper naturally skips spaces. If the string becomes empty after removing spaces, there's nothing to convert, so we return 0 immediately. We set up two variables. Sign starts as 1, meaning the number is positive unless we detect otherwise. Index tracks our current position in the string as we read characters one by one. We create a long called result to store the growing value as we parse digits. We use long because it helps prevent overflow while we build the number. We'll clamp it back down to int later if needed. We store the length of the string in n so we don't repeatedly call length inside loops, just a small efficiency boost. This comment tells us we're about to check whether the number has a leading plus or sign. We check whether the very first character is a plus or minus sign. Here we set the correct sign. If the character is, we set sign to -1. Otherwise, it stays at +1. We move the index forward so we skip the sign character and start parsing actual digits next. This begins our digit parsing loop, as long as we haven't reached the end of the string, and the current character is a digit. We keep reading and building the number. Time complexity. This loop runs once per digit, so the parsing step is ON, where n is the length of the numeric portion of the string. We convert the current character into its numeric value. For example, the character 7 becomes the integer 7. This grows our result. We shift existing digits left by multiplying by 10. Then we add the new digit at the end. It's the same process as writing numbers on paper from left to right. A reminder that our next step ensures we don't exceed integer limits. If the number is supposed to be positive and result goes beyond the largest int value, we clamp and return integer.max_value. Similarly, if the number is negative and its magnitude goes beyond the allowable limit, we clamp and return integer.min_value. We move to the next character to continue parsing. Finally, we apply the sign, positive or negative, and cast the result back to an integer. This gives us the correctly converted integer value. And that's how this algorithm works. It first trims whitespace, handles optional signs, then safely parses digits one by one while guarding against overflow. Solution 1. Test case 1. Let's test our function using this input, 42. This string represents a simple, clean numeric input, no spaces, no signs, and no tricky characters. It's exactly the type of input myAtoi is designed to parse into an integer. Here's how the algorithm handles it. It begins by stripping leading spaces, but there aren't any. There's no sign at the beginning, so the default sign stays positive. The loop processes each digit. 4 becomes 4, result becomes 4. 2 becomes 2, result becomes 42. There's no overflow, no invalid characters, and the parsing finishes cleanly. And that's exactly what our program outputs, 42. And the expected value is also 42, meaning the parsing was handled perfectly. So, our implementation is correct. The algorithm successfully converts the numeric string into an integer using a safe and clear parsing loop, efficient and accurate. Now let's try another implement approach using solution 2. Here we import Java's regular expression tools, pattern and matcher. We'll use them to efficiently extract the numeric portion of the string. We define the solution class, which will contain our regex-powered version of myAtoi. This method, myAtoi, takes a string and converts it into a 32-bit signed integer, following rules similar to C's atoi. We remove any leading spaces from the input string, so we start parsing at the first visible character. This mimics the behavior of ignoring whitespace before reading a number. Here we create a regex pattern to match a number at the very beginning of the string. Caret enforces that matching starts at position 0. Plus, optionally matches a sign. \d plus matches one or more digits. This means the pattern extracts the longest valid integer prefix. We create a matcher object m. This will attempt to find a number in the beginning of the cleaned up string s. If no numeric pattern is found at the start of the string, we immediately return 0. This handles cases like words, hello 123, or plus. This extracts the exact substring that matched the regex, essentially the raw number we're going to convert. We declare a variable num as a long. Using long allows us to detect overflow before we convert to int. We enter a try block because attempting to convert a very large string number into a long may cause a number format exception. We parse the number string into a long. If num_str represents something huge, like 100 digits, this call will throw an exception. If parsing fails, it means the number is too large to fit in a long, so we handle overflow here. This line decides which overflow limit to return. If the number started with return integer.min_value, otherwise, return integer.max_value. This follows the problem's rules for overflow behavior. Now that parsing succeeded, we check whether num is less than the smallest possible 32-bit integer. If so, clamp the value to integer.min_value. Next, we check if the parsed number is too large. If num exceeds the upper limit of a 32-bit integer, we clamp it to integer.max_value. Otherwise, the number fits safely within integer bounds, so we cast it to an int and return it. And that's how this algorithm works. It first trims whitespace and uses a regex pattern to cleanly extract just the numeric portion, then safely parses the number while handling overflow conditions. Efficient, simple, and elegant. Solution 2. Test case 3. Let's test our function using this input. 1337C0D3. This string represents a number followed by non-numeric characters. Our goal is to extract the numeric portion from the beginning and convert it into a valid integer. Here's why the solution works. The regex pattern plus, \d plus looks only at the start of the string. It matches an optional sign, followed by one or more digits. In this case, the pattern matches 1337 and stops when it reaches the non-digit letter C. The algorithm then extracts 1337, parses it safely into a long, ensures it fits within integer bounds, returns it as a normal int value. Everything after the numeric prefix is ignored, as required by the atoi rules. And that's exactly what our program outputs, 1337. And the expected result is also 1337, confirming that the regex-based parsing logic works perfectly for mixed alphanumeric strings. So, our implementation is correct. The algorithm successfully extracts and parses the leading numeric portion of the string. Efficient, accurate, and reliable. So that's our deep dive into string to integer, or the famous atoi challenge, a classic test of precision and control under pressure. Breakdown recap. We started by understanding the task, turning a messy string into a clean 32-bit integer while handling whitespace, optional signs, random junk, and possible overflow. It's all about disciplined parsing and staying within boundaries. Assess recap. We looked at how a single left-to-right scan can get the job done efficiently, keeping track of sign and digits while staying mindful of integer limits. No fancy tools, just logic and order. Structure recap. Our plan was simple: skip spaces, catch the sign, read the digits, and carefully check for overflow before updating the result. Each step built naturally on the last, leading to a clean, predictable flow. Implement recap. We coded it up, ran it on LeetCode, and everything executed perfectly. No errors, no surprises. Check recap. After running through all the test cases, the logic held up across edge inputs, from empty strings to overflows, confirming our approach works end to end. The big takeaway? Even simple-looking problems can hide layers of complexity. The key is calm, structured thinking, step by step, just like parsing this string into a solid integer.